All right, so this is going to be lesson 8.3, resistivity of a wire. All right, and so in 8.2, we talked about resistors. And so resistors are anything that uses electricity, that has electricity running through it. So for example, the microphone that I'm using right now, the laptop you might be using right now, your phone, right? It's a resistor. And resistors have atoms in them, right? And these atoms obstruct the flow of electrons. Well, how much the material or how much the resistor obstructs the flow of electrons, well, that's called resistance, right? So the more resistance you have the electron flow, the lower the electric current. And resistance is measured in ohms, right? And so, but, well, how does your resistor get electricity in the first place? Well, it comes through a wire, right? There must be a wire connected. For example, the outlet, right? You connect the wire to the outlet, and whatever thing you're connecting it to turns on or can turn on. Well, wires also have atoms in them, and just like and the atoms in this wire will also obstruct the flow of electrons. Right? And so the formula for the resistance of a wire is R is equal to that P there, which we're going to call rho, times L over A, right? And so the length of the conductor is L, and A is going to be area, which is meters squared, right? That's the unit for area. The unit for L is meters, and the unit for rho, that P right there, is ohms times meters. Now, that rho there, that P, is something we call resistivity of a material. And whatever wire, right? It could be a copper wire, nichrome wire, could be a gold wire, aluminum wire, tungsten wire. These wires have a very different atomic structures. And so the arrangement of the atoms in each of these materials, there's an innate resistance to electron flow, and resistivity is the measurement. Well, how well does this material resist electrons? So we're gonna watch this video.
In this video, I will explain electrical resistance. Resistance can be understood simply as the opposition to the flow of current, where current is the movement of charge. In a metallic conductor, the moving charges are electrons. Consider this model, where the electrons are represented by marbles, which flow along the length of a wire, demonstrated by the Jenga blocks. Energy is provided by elevating the table, or a battery supplying a voltage to a circuit. When energy is supplied, the electrons flow through the wire. This flow of electrons is current. It took just over 6 seconds for some number of electrons to pass a point. This is an arbitrary value of time, but it is representative of how much current is flowing, since current is how many electrons pass a point in a certain time. A longer time means a smaller current. Therefore, any resistance to the flow of electrons will decrease the current, demonstrated by an increase in time. The next thing to consider then is what determines the amount of resistance. It can be determined experimentally that resistance is equal to the resistivity times the length, all divided by the area, where resistivity is a material-specific value. So according to this equation, increasing either the resistivity or length will increase resistance, whereas increasing the cross-sectional area will decrease resistance. Let's test this. We have increased the wire's resistivity by adding in obstructions, just like a material's lattice structure. The electrons collide with these obstructions, impeding their flow.
Right, you can
This
think of the
time,
red
they
balls as
took 11
atoms.
seconds to pass through the wire. We have decreased the current by increasing resistance. Now, let's increase the area of the wire. This only took 3 seconds. The electrons have more room to move. Increasing the length of the wire simply means the electrons will collide with more obstructions. You can see here that the electrons at the back had to pass by two obstructions to reach the end, whereas the electrons at the front flowed through unobstructed. A resistor can be considered to be a wire with a known amount of resistance. Here, we have reduced the width of the wire in one spot, representing the presence of a resistor. The electrons took 11 seconds again, and you could see where the flow was restricted at the place of the resistor.
Right. So, and that's really how all those things relate to each other, right? So if you double the length of your wire, what's gonna happen here is that your resistance will also double, because again, R and L are directly proportional. They have a linear relationship. And because they're both on the numerator, if we increase the length, we also increase the resistance. And on the area, on the other hand, R and A are both inversely related to each other, right? So R and A, well, if my A increases, my area increases, my resistance will decrease, right? And so that's an inverse relationship, right? Now, here's the thing, right? I'm sure you all have phones. Thing is, something that happens as you run electricity, as you run electrons through a wire, is that these electrons kind of bump into these atoms. Well, when these electrons bump into the atoms, they generate friction, and well, what happens is that the material heats up. As you guys can see in the GIF in the middle on the bottom, right? As you run electric current through something, you kind of heat the metal up. And that really leads to one of the most simplest inventions, right? Which is the hair dryer. And on these hair dryer are these wire coils. Well, if you run electricity through them, right? If you run electricity through them, you're gonna start generating. You're gonna start making the wire hotter. And well, when you make the wire hot, you bring in cold air through the back, you heat that air up, and out comes hot air, with which to dry your hair. And a hair dryer is really one of the most simplest inventions. But because you're increasing the temperature, right, these atoms in the wire, they vibrate more. And when these atoms vibrate more, right, and these atoms vibrate more here, well, the vibration of these atoms kind of get in the way of the movement of the electrons. Right? The electrons are now bumping into these atoms more often, thereby reducing the electric current. So the more the atoms vibrate, the hotter the temperature, the slower your electric current, or rather, the lower it is. And the lower your electric current, the higher the resistance. So as your temperature of the wire increases, the resistance of that wire also increases. Right? So as the temperature increases, the resistance also increases. Let's look at this.
Let me show
But
you
you guys
something.
can watch this on your own time. I'm gonna skip 2 minutes of watching it with you guys because it's not as important. It's cool to watch though. You should watch. It's on the topic videos right here. MIT Physics exploding wire and resistivity.
Let
You
me
should
show you
watch it
some.
though. I'm not gonna watch it with you. And so now we get to your reference table row, right? So on the 4th page of your reference table, on the bottom there, you should see the different resistivities of 6 different materials at 20 degrees Celsius. The reason why it's important is because at 20 degrees, well, we just measure the resistivity at room temperature, right? So 20 degrees Celsius is really just room temperature. So as the temperature increases, my resistivity will also increase, right? Because again, you make these atoms vibrate more, and the innate material's resistance to electron flow resistivity increases. And so now we get to the first practice question. Compare the resistance of an aluminum wire at 20 degrees Celsius, the resistance of a tungsten wire of the same length and diameter at 20 degrees Celsius is approximately what? Well, if you take a look at your reference table, right, we see that tungsten. Let me just make this little bit smaller. We see that tungsten, let's see, aluminum. So rho of aluminum is 2.82 times 10 to the negative 8 ohms times meters, and tungsten tungsten is 5.6 times 10 to the negative 8 ohms times meter. And you'll see that when you compare the resistivity of tungsten to aluminum, you'll see that tungsten is twice the resistivity of aluminum. But we know from the formula itself, right? R and P are both on the numerator. And so both of these, they are directly proportional. They have a linear relationship. So if one increases by a certain amount, a certain proportion, the other will also increase by the same proportion. So if my resistivity here is doubled, my resistance will also be doubled. All right. This question right here says compare the resistivity of a 0.4 meter length of copper wire. The resistivity of a 0.8 meter length of copper wire is what? Now, this is a tricky question mainly because students don't really read, right? And so the question's asking you for resistivity, right? They're asking you to compare resistivity. But this is the same material wire. This is the same material wire. It's copper. And we know that copper wire, the resistivity of a copper wire really is that number at 20 degrees Celsius. Right? And so if we're not changing the temperature, the resistivity of copper wire will always be the same. So the answer here is B, the same. Students don't really read, and so they think that they're asking you to compare the resistance, and they see that, well, you double the length, so I must double my resistance. And that's really the most common mistake students make. The question is not asking you about resistance, the question is asking you about resistivity. All right? So this question is also a proportion question. Right? So you have aluminum wire of length 1 meter has a resistance of 9.0 times 10 to the negative 3 ohms, and that's really the symbol for ohms. And if the wire were to cut into two equal lengths, each length would have a resistance of 1. So here I'm having my length, right? I'm having my length. But we know that from the formula itself, we know that L and R are directly proportional. We know they're both directly proportional because they're both on the numerator. So if one increases by a certain proportion, the other will also increase by the same proportion. So if I have my length, what's going to happen here is I'm going to have my R. And well, my original resistance was 9.0 times 10 to the negative 3 ohms. So if I have my R, my new resistance of this wire that's cut in half is going to be this divided by 2, which gets me 4.5 times 10 to the negative 3 ohms. 5D. So we have a diagram here, right? And really, again, you see this diagram. This diagram really means that this is a battery, right? So you have a voltage of 12 volts here. The variable resistor is a nichrome wire. So a nichrome wire has a resistivity of 150 times 10 to the negative 8. 150 times 10 to the negative 8 ohms times meter and maintained at 20 degrees Celsius. The length of this wire may be varied from 10 centimeters to 90 centimeters. And the ammeter here reads 2 amperes. So you have a current, you have an electric current of 2 amperes. When the length of wire is 10 centimeters, so you have a length of 10 centimeters, and you convert it to meters. Well, how do I convert it to meters? I'm just going to move that decimal place over 2 spaces. And now they want to determine, well, what is the resistance of this wire? I know most of you guys are going to jump to this formula right here, right? So, because that's a formula we've been using for a while. We can't use this formula though, because we don't have my area. Right? We have my resistivity rho, we have L, we have R. Well, we're looking for R, but we don't have A. We don't have my area. But what we can do here is you can use Ohm's law. Right? We know that the voltage of this circuit is 12 volts and the current of this circuit is 2 volts. And so 12 divided by 2 here is going to give you 6 ohms. And that's how we can determine the resistance there. But now this question is asking us to, well, now we want to calculate my cross-sectional area. Right, now that we want to calculate my cross-sectional area, I'm actually going to, I'll make a new one. Okay, hold on, let me just get the values here. So we know my voltage, it's 12 volts, right? So for the last problem, current is 2 amps. The resistance we calculated was 6 ohms. What was the other one? Oh yeah, the length. The length was 10 centimeters or 0.10 meters. And the resistivity of nichrome was 150 times 10 to the negative 8 ohms times meter. And you want to know what the cross-sectional area is. So my resistivity is that, right? And I want to solve for A. So let me just plug everything in. My length is 0.10 over A. That's what we want to solve for. Multiply by A on both sides. We get 6A. And I'm really just going to simplify this top part of the numerator. This 150 times 10 to the negative 8 times 0.10 is going to give you 15 times 10 to the negative 8. Divided by 6 on both sides, and then well, A gets me 2.5 times 10 to the negative 8. And the unit for area is meters squared, right? So that is going to be my area. All right, that's that.